What is ground effect and how does it work? I want to try to answer those questions in this video, mostly with the help of some fluid simulations of air flowing around a wing that I've performed. This is of course a simplification compared to an entire aircraft, but makes the results more generalizable. As for the simulations, I am comparing the ground effect scenario, which would be takeoff or landing, to a free flight scenario. If you've heard of ground effect before, you may have heard of it anecdotally from pilots. They're talking about the reduced drag when under the influence of this effect. We will see that this is partly true, but there's more to it. There's definitely an efficiency gain, which can also be seen by certain ground effect vehicles made especially for this zone of flight, such as the Ekranoplan, which was rather famous on YouTube a while ago. Let's start by looking at the free flight simulation. This is the free flight scenario. The freestream velocity is 50 meters per second. This is less than most planes would have in free flight, but this allows me to keep the simulation as incompressible, meaning that I can assume that air density is constant. The simulation has 2.5 million cells, around 2.5 million. I would consider this as a rather low or at least medium quality simulation, so I wouldn't put too much faith in the numbers. This is just because I have to run this on a laptop. What you can see here is a 2D slice in the center region of the airfoil, showing the velocity magnitude. It is fairly hard actually to describe the velocity and pressure distribution around an airfoil, and it's not entirely intuitive. I'll just give a super basic explanation here to not bore the people that already know about it. The way to look at the top side of the airfoil here is to look at it like you would nozzle in a water hose. Of course, the airfoil is not completely round or sealed off, but the example still kind of works. In the hose nozzle case, you have a restriction of the cross-sectional area, and with a restriction of cross-section, the flow velocity increases. At the same time, you also have high pressure in the hose, and then the pressure relaxing to atmospheric conditions at the end of the nozzle. It is similar here that we have a velocity increase over the top side of the airfoil while having a pressure decrease. There's a nice and simple formula we can use for incompressible flow when neglecting viscous effects, as we can do in most of the flow, which basically describes as pressure decreases, velocity increases, and vice versa. Basically describes the conservation of energy when neglecting things like potential energy. In this hose analogy, the bottom side of the airfoil could then kind of be seen as more of a diverging part here with a slight angle upwards, meaning our cross-sectional area increases and our velocity therefore decreases, which then in turn with our formula here means our pressure increases. Before we look at the pressure plot, I want to look at two more sections here. We have the so-called stagnation point at the leading edge, which is kind of intuitive. We have a decrease in velocity because of the blunt nose shape, not describable by our simple Bernoulli formula due to viscous effects, is the reduction in velocity here at the trailing edge, this blue and green area. This is due to friction effects with the airfoil and can also be a slight separation of flow. This is the static pressure distribution. As you can see, it is inverted as expected. We have low pressure on top, then high pressure on the bottom back side. As you can see, the area of reduced velocity at the trailing edge is not visible in a pressure plot. As I said, it cannot easily be described by the Bernoulli equation. The pressure distribution is also a good way to get a feel for lift, and is one of the ways for explaining lift. We have low static pressure on the top side of the airfoil, and then we have a higher pressure on the bottom of the airfoil, or at least in parts of the bottom of the airfoil. We have a sort of dual effect here. The top side of the airfoil gets sucked up by the low pressure zone above the airfoil, while the bottom side gets pushed up due to the high pressure zone below it. The bottom side of the airfoil is not always a higher pressure zone than the surrounding air, but if you want to create lift, it always has to be at a higher pressure than the top side of the airfoil at least. Since what we care about is the pressure distribution right at the wall, so right at the airfoil, we can create a two-dimensional plot of the pressure over the chord length. So this is the 2D pressure plot. I've chosen a span-wise position of 0, so right at the end of our domain, where our aircraft hull would normally be. You can see the points seem to form two different lines. The line that is predominantly on top is our upper airfoil surface, and the lower surface is the lower line. You can see the y-axis, which is the pressure difference compared to atmospheric, is flipped to enable this effect. What is also oftenly done is that the pressure difference isn't plotted, but instead a dimensionless pressure coefficient to be able to compare results between different simulations or experiments more easily. At the leading edge or the stagnation point, we have a very high pressure, which then rapidly drops off in both cases. On the upper surface, it stays at a lower pressure for a longer amount of time. It looks like it almost stays flat, and the lower surface then drops off over time until they meet again at the trailing edge. When extrapolated along the span-wise direction, this pressure difference, so the area between the two curves, can be seen as a force. This pressure force mostly acts in the y direction, so the direction where our lift is pointed. There's also a small component acting in x direction. This is just due to the fact that pressure always works normal to the surface, and our airfoil is curved. You can see we have a fairly large closed-off area between the two curves, which would generate positive lift, and then have a smaller area close to the stagnation point, close to the leading edge, which creates negative lift. Why am I showing you this curve? Well, we are still on track for explaining the ground effect. If I plot the pressure distribution at different span-wise locations, you can see that as we get closer to the wingtip, the large area between the two curves decreases in size. So the pressure difference between the two curves gets less and less. You can also see that the area corresponding to negative lift does slightly increase. What does this mean? This means we have some kind of three-dimensional effect. We can't just extrapolate 2D results onto our 3D wing. This 3D effect is due to pressure equalization over the wingtip. We know we have high pressure below the wing and we have low pressure above. And this pressure difference causes airflow from the bottom of the wing to the top side, creating so-called wingtip vortices due to the fact that we still have a velocity component in x direction. When looking at the simulation, you can see exactly that. Path lines are plotted here, so lines that individual particles will take, and you can see that they go from the bottom surface and curve up to the top surface, then creating a swirl. You can also see that the path lines close to the wingtip going over the wing get pushed slightly inwards. So we also have a kind of three-dimensional effect here, which then relaxes as you get closer to the root of the wing. This phenomena reduces the effective angle of attack that your wing sees and also creates drag known as induced drag. Since this drag would not exist if there was not a pressure difference between top and bottom side, this drag is also known as drag due to lift and gets stronger as our lift increases, meaning the pressure difference increases. What I wanted to show here now is results of a different software that I also used. It's XFLR5. This is the same wing setup as in ANSYS. The difference here is that I removed the symmetry condition and now made the wing 6 meters long, so we have 2 tips. XFLR5 is made mostly for inviscid simulations, meaning effects like separation and friction are not looked at. There are some formulas for estimating them, but definitely not as accurate as the other simulation. However, what you can see here is our lift distribution over the wing. You can see it gets reduced as we get closer to the tips, and you can also see the simulated streamlines here with the wingtip vortices. I also wanted to use this additional simulation as a sanity check to see if the more complex simulation gives similar results. To do this, I compared the lift coefficients, seen here as CL. If I compare the two coefficients, then there's a difference of around 6 to 7%. So not horrible, but definitely still a relevant difference. As you may be able to see, the program also gives out a drag coefficient. However, I would not trust that value due to the fact that the program is not meant for looking at viscous effects accurately. Finally, we arrive at the ground effect simulation. So first of all, here we have a comparison of the static pressures. On the left we have the wall case, on the right side we have the free stream case. They look pretty similar to begin with. The only difference I could spot is that on the bottom surface the blue region is smaller in the wall case and the yellow region is larger, meaning our high pressure region is larger and our low pressure region is smaller. So generally we have a higher pressure on the lower side, and I wasn't able to really see any difference visually on the top side. Now, colors aren't the best way for comparing the cases, so I plotted the pressure again of the wall case compared to the free stream case. As we expected from the images, you can see that the lower surface now has a higher pressure in the wall case. Interestingly enough, we can also see that the upper surface has a slightly less negative pressure, meaning the pressure is also a bit higher. Another factor is that the suction peak on the bottom side that we saw in the free stream case is now strongly reduced, meaning we have a larger area that contributes to positive lift, and our area that contributes negatively is now almost zero. This confirms what is talked about in literature. Basically, we have a higher pressure air cushion forming under the wing due to the ground in close proximity. Now I was interested in what happens at a tip, so this is at a spanwise location of 2.9 meters. As I said, the wing is 3 meters long, so almost exactly at the tip. And as you can see, there's almost no difference between the cases. This was very surprising to me, since the other factor mentioned in literature is the reduction of the strength of the wingtip vortice due to the ground in close proximity. From what I could tell, this is even often cited as the major contributing factor, and I thought this would show up in the static pressure distribution. So this unexpected lack of change made me look at the vortices more closely. This is a visualization of the path lines flowing over the airfoil in the free stream case. What can we see? Well, we can see that the path lines that even originated in the more central region of the airfoil are also influenced by the vortex. They also curve towards the vortex. And in general, streamlines or path lines that we would normally expect to stay in one plane are lifted out and twisted outside of the plane, meaning our vortex has both a large horizontal and vertical extent. An important thing to note, though, when comparing to the wall case now, is that the path that our vortex core has is mostly parallel to the free stream. Looking at the wall case now, we can see that the vertical extent of our wingtip vortice is way lower than in the free stream case. Generally, the case looks more flat, and it looks like our vortex in general is smaller. What we can, however, see as a difference is that our vortex core is curved towards the left side. It is no longer really straight as it was in the free flight case. Again, I wasn't too happy with the visual inspection, so I thought about a way of estimating the strength of the vortice. What I did here was I first of all plotted the static pressure behind the wing at a distance of 2.5 meters for both the free flight and the ground effect case. What you can see here is that where our vortex core is, the static pressure drops significantly. I used this for estimating the strength of the vortice. What I did was create contour lines around a static pressure difference of minus 50 pascals for both cases, and then exported those cells to plot them. Here you can see the cell positions from the 50 Pascal ISO line for the wall case and the freestream case. First of all, I couldn't do that much with just the points, so I did some regression to find a circle for both of the cases. Looking at the rings, first of all, we can see that our wall case is indeed curved slightly outwards. Remember that now we are basically looking at the front of the airfoil compared to the previous pictures where we were looking at the airfoil from the back. So as we move right, we curve away from the airfoil, and we can also see that the height of the vortex core is increased. This makes sense since we have the high pressure area and the ground as an obstacle. To estimate strength, I wanted to calculate the area of these circles, and I found out that there's an area reduction from the free case compared to the wall case. The wall case is 85% of the area of the free case. So that could be an indicator of reduced vortex strength. Coming now to a final comparison of the cases, a good parameter to compare for aerodynamic efficiency is the lift-to-drag ratio. In the free flight case, we have a lift-to-drag ratio of around 18. In comparison, in the ground effect case, we have a lift-to-drag ratio of 25, so a massive improvement. This comes, as we expect, because of the increase in lifting force, but also, interestingly enough, the drag is strongly reduced, and I checked this is almost all due to a reduction in pressure drag. As a conclusion, we can tell that, at least in this scenario, the ground effect does lead to massive increases in efficiency. However, if I were to run this experiment again, I would try to increase the strength of the wingtip vortice to hopefully see clearer changes in that regime. I would probably do this by increasing the free stream velocity and also increasing the angle of attack